Hi folks, welcome back. I am here to record the remainder of the lecture that was given on Thursday, January 25th, where my recorder stopped working halfway through for reasons I still don't understand. So we were talking about alpha, and I am picking up on lecture 3, slide 18. So the computation of alpha involves variances and covariances. In particular, two quantities, the sum of the indicator variances and the variance of the indicator's sum, which are not synonyms. The first one on the top here, sum of the indicator variances, is literally just the variance of each item added together. So that is a baseline for the expected amount of variation. The variance of the indicator's total score includes the covariances among the indicators as well. So we have not only the variances, but all possible covariances, each multiplied by 2, because the covariance matrix is symmetric, so the same covariance shows up in two different spots. The formula then, by which to compute alpha using that information, has the variance of the total score minus the sum of the item variances, divided by the variance of the total score. So what the numerator essentially reduces to is the covariance among the items relative to the variance. And if items have a lot in common, then most of their variability should be in common. Yeah, let's go with that. And if you're thinking to yourself, looking at this formula, is there an easy way to do it? Yes, there is. We can do it in correlation form. And there are two components to alpha in this version of the formula: the number of items and the average inter-item Pearson correlation. So that means given enough items, you are going to have a good enough alpha. And as we said on the previous slides, the big problem with this is that alpha assumes without testing that the indicators are all measuring one thing, that they are unidimensional. And we will, throughout the semester, learn how to do this using latent variable measurement models instead. Why alpha has to assume this is because there's nothing in the formula that takes into account the spread of the inter-item correlations, or their standard deviation. You can think of it that way. So there could be pockets of correlation amongst the indicators where some are more related to each other than others, and because we're only looking at the average, we wouldn't know that. So the fact that alpha is assuming that the indicators are measuring only one trait is the biggest problem. Beyond that, it's assuming that all the indicators measure that trait equally well, that they have equal discrimination, or synonyms tau equivalent or true score equivalent with uncorrelated errors. So to make this point a little more concretely, here is a table from one of your readings. It's a book chapter, and they describe two different scenarios. So on the left-hand side, test A has 10 items that are all equally correlated. Okay, that looks pretty unidimensional to me. Test B, on the other hand, has only 6 items, and there's clear pockets here, where items 1, 2, and 3 are more correlated with each other, 4, 5, and 6 are more correlated with each other, and then the cross correlation is a bit lower. Alpha, for each of these scales, these correlation matrices, is 0.81. It's the same. But test B clearly looks like it's 2 dimensions rather than 1, and alpha doesn't have a way to tell us that. So we have to keep in mind that these methods of computing reliability that rely on assumptions, they don't make any sense if the assumptions aren't met. It does not make any sense to compute an alpha for a multidimensional trait. So that's going to be the first thing that we do, is verify our dimensionality, get evidence that it's as we think it should be, and then we can talk about how reliably each trait is measured. Some more examples then. You can rearrange the alpha formula to, given alpha and the number of items, compute what the average inter-item correlation had to have been. That can be useful to do in published work, for instance, that people give the alpha and the number of items. Here's an example from real life. The 2020 GRE Psychology subject test reports an alpha of 0.95, and it's using a method called KR20, which we'll talk about next. But if you do the math, given that there were 205 items on this test, the average intercorrelation was 0.084. So less than 1% of the variance in common across items. That does not sound like a unidimensional measure to me. It's pretty easy in practice to get a decent alpha if you have enough items. And during class, I surveyed folks and asked what is the standard for what a good enough alpha is in each of your fields. I think it's 0.8 is what I see most commonly. Other people said 0.8. A few folks said 0.7 or even 0.6 can be acceptable. You can get to 0.6 or 0.7 pretty easily if you have only 8 items and the items have an intercorrelation on average of 0.2. Now keep in mind this is R. If we think about this in terms of shared variance, then it's even worse because R squared is 0.04 if the correlation is 0.2 on average. So we're talking 4% shared variance and then 96% something else that we don't know what that is. So not very compelling. And here's a chart that makes the point that even if you have a very low inter-item average correlation, you can get up to a conventional level of alpha if you just keep adding items. So this is why I don't like items, or I don't like alpha, excuse me, is that if you have a good alpha, it doesn't necessarily mean you have a good measure. If you have a bad alpha, however, that is a problem. So I told a story in class, true story, a former student whose dissertation committee I was on. She had a measure that had 5 items, and she computed an alpha, and it was negative. This actually happened. You can have an alpha of 0 or it can even go negative because that means there are negative relationships. As one item goes up, the other goes down. And I didn't believe her at first, and we double checked it, and yeah, it's negative. It's really that bad. And I told her these are 5 different things. You can't think of these as indicators of a trait. She reported that back to her advisor and came back and said that she was told, no, you are going to add these together. That is what we do in our field. I decided to not push the issue. I let her graduate, add things together. Sure enough, she did not have any significant relationships. So, and of course my computer wants me to restart while I'm talking again. I love how it always does that. So, point of the story, a good alpha does not mean you have a good scale. Here is another way that alpha can be computed. This is called the KR20, and that is because it comes from equation 20 of a 1937 paper. I told you at the beginning of class that these methods are not that modern, and I am not wrong. This is just a computational shortcut to computing alpha if you have binary items. It's not a different measure of reliability. It relies on the same information, means, variances, and covariances. Because the variance is determined by the mean, in binary data, you can shortcut the formula. It's the same thing, though. And this is how reliability is computed for the GRE subtests. The last time they had documentation on their website, I've also seen it in several other standardized test documentation systems. The problem, though, is that Pearson correlation, or KR20, using Pearson correlation, is going to be limited in terms of the reliability that it can possibly be. Because the mean and variance are dependent in binary data, that is going to limit the possible correlation that 2 binary items can show. It's only going to have a maximum of 1 if both items have a mean of 0.5. So this table shows you some examples of what can happen. If you have a mean of 0.1, so only 10% of the sample had a 1, 20% of the sample had a 1 in this other variable, your maximum correlation is 0.67. It is far lower than 1, and it gets particularly bad if they're skewed in opposite directions. So it is not the best way to measure association in binary data to use Pearson correlation. What can you do instead? There are choices. So I wanted to introduce synonyms that you will see in the literature for Pearson correlation. If it is between 2 binary variables, it is sometimes called, and we took a vote, phi or phi, and I made the joke, phi, phi, pho, fum, I don't know which one it should be. So phi, phi, who cares? Doesn't matter. It's the same thing as Pearson. It's just a computational shortcut. Same idea behind the point by serial. That's binary and quantitative using the Pearson formula. Perhaps a computational shortcut, but it's the same information that's being used to compute reliability. The other ones are different. So these rely on the concept of an underlying latent distribution that gave rise to the observed binary response. So a tetrachoric correlation is supposed to be the correlation of the underlying variable that gave rise to the binary response in which the underlying variable is actually continuous. You have to believe that that underlying variable is normally distributed, but since we haven't measured it and there's no way we could possibly know, that's fine with me. And I used paint to draw a picture of what tetrachoric correlation would look like. So since I got to do that last time, I'll do it again. Why not? Everyone loves paint, right? So if I have, oh, that's a very big x-axis. We'll make that a little bit narrower. So if I have a classic plot here, scatter plot, and I wanted to show a zero correlation, I might draw a plot like this, where there's just a cloud of points, okay? And an alternative plot for what a perfect positive correlation would look like would be something like this, where the points pretty much fit onto the straight line. An equally strong negative correlation would have the points going down the other way, okay? So what we have, though, is a contingency table of binary responses. I'm going to need to make this a little bit narrower. Hang on, let's go down a little bit. There we go, it's good. Where this is the 0 cell, this is the 1 cell, and the same up here for these. 0 and that's 1. Okay. So if these two binary items have no relationship to each other, we might expect relatively equal distribution across these cells. So that is comparable to this picture down here. It's like we take this and try to figure out how much proportion of the bivariate normal distribution would be in each of these cells given the correlation underlying the data. So if I have a picture like this, that would be consistent with the contingency table where everybody is in this cell or that cell. Likewise, a negative correlation would be consistent with the contingency table of everybody in this cell or that cell. So you, in this case, we are trying to estimate what the correlation would have been that created these contingency tables. That's the idea of tetrachoric correlation. And polychoric correlation is the same idea for ordinal, where there's just more cut points. So you would take this, make it look like a tic-tac-toe board, essentially, and you can figure out the area under each of the combinations. Biserial we're not going to use this semester, but tetrachoric and polychoric correlations are the basis of what's known as limited information estimation for IRT and IFA models. Limited information means that the model is operating on a summary of the data, so the data are summarized into these correlation matrices, and then the factor analysis model is estimated, the parameters are estimated using that tetrachoric or polychoric correlation matrix. That's as opposed to full information estimation, which means that you are using all of the original data, the multi-way contingency table of all possible responses. So if you have binary outcomes, tetrachoric correlation is going to be a better measure of association. The only time it runs into trouble is when you have empty cells, because then it's much more uncertain like what it would be exactly. And polychoric correlation would be the same way. And you'll get a chance to see this when you complete homework 3, in which I ask for Pearson correlations, and then homework 5, I would ask for tetrachoric or polychorics instead, so you can see how different your conclusions would be using different measures of association. All right, this is the point where I decided to transition to the example 3 so that we could look at classical test theory item analysis as well as correlation matrices and alpha and the types of decisions that one might do. So I built this example out of a real study, so the data are not included in the download folder, but all of the inputs and outputs from 4 different programs. I used SAS, Stata, R, and SPSS in this example. That way, when you do these analyses on your own data for homework 3, you can have your choice of software packages to do them in. So I participated in this project as a graduate student at the University of Kansas. I was an RA for the Beach Center on Family Disability, I think it's something like that. They've changed the name a few times, and I'm not sure what it is at this point, but there I am. And I have no content expertise in terms of families of children with disabilities. I was hired because I know how to do factor analysis. So I'm approaching this at the time from very much a data-driven perspective. So the purpose of this line of research was to develop new measures that could be used to understand the quality of partnerships between families and the people who serve their children with special needs, as well as the other aspects of the family. So as part of my work with this group, I participated in the development of this scale, which is the, oh goodness, family, I can't remember the exact name now, it's terrible. Family professional partnerships, something like that. And the other one that I did was family quality of life. So this is the family and child partnerships one. So we had started with a whole bunch of items, refined through exploratory factor analysis into a solution where we have 11 items that we thought would go in the child subscale and 10 items that would go into the family subscale. And this is an ordinal response format where the items range from 1 to 5. So first off, we have Stata. I'm using Summarize to generate descriptive statistics and PWCore to generate a correlation matrix. By the way, regular core does listwise deletion of incomplete responses, and I know that there are some missing responses here, so I use the PW version, stands for pairwise. In R, I did the same thing, but I first created an object that held the names of all of my variables so that I wouldn't have to keep typing them, and then subset the data to just those particular variables. So I used describe from the psych package to get summary statistics, and then core as well from base R. And here are the summaries of these items. So note, yes, not everybody answered every question. That is actually okay in latent trait analyses. If you were to compute a sum score, though, when some people have incomplete data, that's a bad idea because the sum will be lower for people who have fewer items contributing to it. Instead, if you compute the mean across items, then you're assuming that missing responses are missing completely at random, which is what it sounds like, relative to the assumption in latent variable measurement models, which is missing at random or conditional on the information and other responses that you do have for that participant. So that's usually a more reasonable assumption, but unfortunately it's not a testable one. So the first thing that I wanted to point out is that we have this ordinal measure, 1 to 5. The median of every response, every item is 5, and the means are in the 4s. So I don't need to look at a distribution plot to tell you that these items are skewed. They are not normal, and they are certainly not continuous. So right off the bat, these, the factor analyses that we did, exploratory factor analyses, and then confirmatory factor analyses in this paper, these are not the right ones for this kind of data, but they were what I knew how to do at the time, and so that's why we use them. Here are the Pearson correlations across these indicators, and I threw the correlation matrix into Excel to do conditional formatting, which I really like because it makes things a lot easier to process. And the highest values here on the diagonal, those are the standardized variances of 1, and so then the correlations that are redder are lower in this plot. And what I see here is nothing that is a huge red flag. So the items are correlated. That is step 1. If your items aren't correlated, it is game over, and there's no possible way that they can be part of the same factor measuring the same thing. It does look like some of the items might be worse than others, so I see some lower correlations for item 14. I see little pockets of higher correlations here. So it looks like an empirical question whether these patterns are consistent with a one-factor model in which some items just simply are more discriminating than others, or whether there might be multidimensionality here. But at least I have a decent strength of correlation to start with, and these numbers, by the way, are probably downwardly biased because, again, they're Pearson correlations, whereas polychoric correlations would have been a better measure. But we'll get there. So I have some classical test theory statistics printed using the alpha command within Stata here, and we'll look at the content of the items in just a second, but I wanted to point out, so we have the sample size. Item test correlation is the correlation of the item with the total score, including that item, so it's inflated because it's partially correlating with itself. That's why people typically look at the item rest, or item remainder correlation as it's called, which is the correlation of each item with the sum excluding that item. And these are our indices of discrimination, how related the item is to the trait that it measures, in which we are using the total score to substitute for the trait. And these numbers are pretty decent. I don't see anything that's super low. Anything that is close to 1 is good. Anything that is close to 0 is not so good, especially if it were to be negative. And this last column is badly labeled. This is not alpha, because alpha is one number, which is down here, which is 0.91. No, this is the cheat code for alpha. This is alpha if deleted. These are the values that alpha would take if that item were removed. And so what you would look for in this column is the removal of any item that makes alpha higher than what it is currently would indicate that that is not a good item. So none of these fall into that category, so that's pretty good. However, I did highlight 2 items here, item 10 and item 14, and I asked the class if they saw anything suspicious with respect to those items in this table. And the answer is no, there really isn't. I mean, this one is a little bit lower in terms of its discrimination, but so is that one, and I didn't highlight that one. The reason that I made a point about these items is that we can't just look at the numbers. We have to look at the content and whether it makes conceptual and theoretical sense. And in this subscale, the focus is supposed to be how the service provider treats the child. It is called the child subscale. And the items that I highlighted do not have child in them. They are more general items. And so from a conceptual point of view, this doesn't really make sense. The reason these items were put into the subscale at this point was because exploratory factor analysis put them there. So, one of the problems with that method, it is not your data's job to tell you what it's measuring, it's your job. So, on the basis of conceptually this not making sense, we decided to remove those 2 items and try them out within the other subscale for family, which is more general. So here's the results for the same 11 items using R and using the alpha package, which I think is from Psych, if memory serves. Converging evidence, alpha 0.91, which would be considered good in any book. The rest of these things are not as useful, so we'll skip on over them. And then we get to the item statistics, where these are very unhelpful labels, but R drop is the item rest correlation. I did find someone else's example that I thought was useful for this, so here's a link to someone else's example. Thank you, whoever made that example for me. So after dropping items 10 and 14, because they were conceptually better fit to the other scale, we have 9 items left. We've rerun the analyses. Alpha is done down a little bit. It went from 0.91 to 0.897. I can live with that. Here are the item statistics. So this is alpha if deleted. There are no items by which alpha would increase if they were removed, so that's good. And the discriminations are variable, but there's nothing that's super concerning here. So I would say this looks pretty good. And then we did a confirmatory factor analysis to verify that it was in fact unidimensional and that the model fit was acceptable. And it should have been an ordinal version of the model, but again, I didn't know what I was doing at that point in time. So, and same thing in Stata, converging evidence with respect to the 9 items looking to be reasonably good. So these introductory level statistics are going to be useful to find giant red flags. If there's big problems with your items, they will show up this way. And no matter how small your sample is, you can always compute these statistics. And so I do think this is perhaps a useful first pass, because staring at a correlation matrix can tell you a lot. And particularly if you group the items by the subscales that you think they go with, you should see block diagonal, chunks of higher correlations in those. And if you don't, then that's an indication that you're not going to get the factor structure back that you think you should. And I believe that was where we left off. So funny that I can do this so much faster when I'm just talking to myself, but it's not nearly as fun. But if you're with me so far, thank you very much for being here, and I hope to see you next week in class. Or just on the internet, your choice. Catch you on the other side.